Hey, how are you doing?
Well,
I We appeared online and we disappeared and we are back now. Okay, great.
yeah, that's a decent summary of the week.
Yeah. If anybody noticed, um, things are like accelerating, if possible, at all in the world of AI. So we ourselves need to accelerate what has been accelerating through our compiler. So we've been very, very busy this couple of weeks. And and so, like, in terms of things to show end to end, it's there will be surprises in the future. Um, Nonetheless, because we will be at GTC demonstrating stuff, so that's very good. So we decided that for this episode, we're gonna focus on, yeah, we saw, us writing transforms and so on, but there's a piece of Thunder that we never talked about. And it's a piece that is, well, we kind of alluded to it a number of times, but it's kind of the core of the acquisition, which is the interpreter. And we will walk through what this is, like what it is for. But it has like a more general validity in the end, right? It's something that is used by Thunder to acquire a model, what a model is doing, but could be used in the future also for other things that go beyond optimizing a model. If you want to track what's happening in a program, in a general program, and so when I'm thinking about agent systems and so on, it's been a few months now that uh, certain things about having systems of agents that call APIs and so on that you need to run, and there's a way where you build them as dogs, or there's a way where you build them as programs, and but then you need to acquire those programs to do something with them. And so I think our interpreter may potentially be used in other places. And so this episode is about that. It's about how do you make sense of a program that a user used, and so that you can understand what it does before it executes. Because the planning and the kind of figuring out what is happening is the core of what Thunder is, and it will be the core of other systems in the
yeah,
future. Um, and I mean, there are many ways of carrying out this task, right? One classical way, for example, JOX, what does JOX do is it introduces some data structures that are tensors or multidimensional arrays that can keep track about what happens to them. And so if you multiply a tensor by a number, that tensor will record that something happened to it, and then will produce some effect in a kind of a stack of operations that gets populated. But what happens if you do not apply something that happening to your program to your tensor, but to something else, like a global variable? And that basically your compiler would be, in that case, JAX, would be colorblind with respect to that change, to that effect. And so that is something that JAX developers deal with, and there's a good way to deal with. There's a section in JAX that says, what is it? The
the
sharp?
sharp bits.
Yeah, the sharp bits. Yeah, if you look it up in the JAX documentation, it will tell you what you cannot do because there are some things that JAX doesn't see for this very reason, because you're tracking what happens to tensors and not what happens to other things like a string and so on.
Yeah, I mean, one thing is whether or not like you can use it and have a valid program, but the other thing is that it's relatively easy to make mistakes there, and it will be silently broken, right?
Yeah,
Uh,
yeah.
uh, so that's a good property if you like see everything what's going on, then you can say, yeah, no, there's something going on that is not good, and can hopefully warn the user about it.
Yeah, because ultimately your acquired program needs to be equivalent to your source. initial program, right?
Right.
So if you're colorblind with respect to certain things, then your program will not be equivalent. Maybe the side effects it has on tensors themselves will be equivalent, but it's up to you to verify it, right? When you compare outputs and so on. So for Thunder, we decided to do something a bit more, a tad more insane, and which is in the good way, of course, which is instead of having things that track what happens to themselves, let's write an interpreter that will interpret what is the kind of ultimate source of truth, which is bytecode. And we'll show you every step right now. So what happens to Python? So let me share my screen. Maybe that will be a bit more visual. And by the way, I forgot my cable today when I was at home. So you will see a slightly different thing, which is my iPad within a Google Meet because I forgot my cable to connect it directly. So if you have a Python program here and you run it through CPython, the thing that will happen here is that the program will be translated into something called bytecode. So here you have your source. It's very human-friendly, human-readable. And the bytecode is something that kind of looks a bit less like something that a human would write. Hey, it has a lot of pushes and pulls, and there's a stack of operations, and you kind of push and pull operations on the stack. It's a very classical bytecode with some specificities for Python. And ultimately, CPython will interpret this and produce effects. So this thing will run in some process that has been originated from a kind of a C interpreter that interprets this bytecode and produces effects. One way of understanding what's going to happen before you execute the full program, or as you execute a version that might not be exactly the same as the full program, is to say, okay, what if instead of just interpreting this with CPython, we take the bytecode, just the same exact bytecode that would be generated in your usual execution, and write an interpreter. It's a custom interpreter that will go from bytecode to the same effects. So, but instead of being CPython, it's our own. And that gives us the ability to hook into the execution and say, okay, now you see this bytecode structure here. Instead of executing these 5 instructions in bytecode and mapping them to, I don't know, appending to a list, for example, instead of appending to a list, do this other thing, or append to the list so that the program can continue, but also record that you're appending to a list with a set of information, right? And so you can keep track of what's happening, 2 things, by actually seeing it happen in bytecode. And so you're saying, okay, now I can say that this program, among the many things it does, it will transform these data structures that I'm interested in into these steps. And once you create this schedule, then you can basically also, for example, in case of Thunder, re-execute this schedule. Or you can execute it, you can fake execute it, not on real tensors, for example. So you won't compute any matrix multiplication here, but just record the fact that it happens. And then once you needed to run it for real, then you won't go through this process again, but you just can re-execute this directly. So this is very, very broadly. Do you want to add anything here?
Yeah, and in addition, you can divert. I mean, the way you get the record is that you divert all sorts of things. And so ultimately, many of the things that are in the bytecode will translate to function calls or method calls of some form and shape. And so one of the things that is we don't actually hook that much into the bytecode execution, but we hook into all sorts of functions. and divert the functions from what they are originally to our own versions. And this is like really powerful. And the trick here is for any of these systems is how thoroughly can you do it? Like if you have a function that you want to override and divert, can you really find every call to it? And so, for example, for simple cases, monkey patching is an alternative to this thing. And for some cases, it's easier. But so the trick is that the monkey patching will only go so far because if you monkey patch, you actually set a member of a module or something. And then, of course, anything that looks up that member from that data structure will get the new thing. But if somebody something either got a reference to it before you monkey patch the thing or has a different mechanism to reach that thing, then it gets tricky. And so having this interpreter really allows us to be very, very thorough because we really see every bytecode instruction that is being executed, as long as we don't let like the execution escape. And we will, we might have something of that too in a bit.
Yeah, and so basically, what is the disadvantage of doing that? Like, why do people not have an extensible interpreter all the time, right? And instead rely on something that is a bit of black boxy like CPython? Well, because it is slow, right?
It's slow, yeah, and it's really slow. Like Python is not famous for being extraordinarily fast. But so writing all the bytecode execution in Python, and doing some administrative stuff around it, that is a recipe to make it really slow. So, for example, for the Llama 1 billion, we had like a minute of wait always when we traced through the full module. And that minute was spent in this Python interpreter. And it's in some ways, it's a bit unfortunate that we have to do that. On the other hand, yeah, you can have all sorts of caching around it. And so we think it's not like that bad. Sometimes there will be shortcuts that you want to take or that pay off pretty heavily if you can take them. And we might have something around that like later on too.
Yeah. In fact, these like deep learning programs are programs that you typically want to run once, but then you repeat the same thing over and over. And so until some inputs change, and we could stay here forever, and we already talked about that. But essentially, what you do is once you build this sequence of things that are function calls and operations in the end with arguments, then you can re-execute them a lot of times, and sometimes you even can kind of shortcut Python entirely. You build a CUDA graph out of the sequence. So there's all sorts of ways to avoid unnecessary computation or unnecessary change of control from the GPU to the CPU and so on.
I mean, the trick in all of this is how do we make sure that, like, when do we expect the thing that we already did to be giving space to the exact same computation?
Yeah.
And that can be tricky at times, right? So, for example, when you have mixture of experts, the classical formulation will be that you like check which expert gets which tokens. And then this will like lead to different programs depending on which experts like see which tokens. And then there is, for optimization, you use a thing called the fused mixture of experts. And miraculously, that also helps for keeping the same code path every time. But
Yeah.
so that is a bit of a theme that data dependent control flow like is the enemy of deep learning
Yeah.
compilers. But
Yeah.
yeah, but we'll see a bit of what are our options here too. We're not going to completely solve it today in the demonstration that we have, but close enough.
Great. So let me just introduce very quickly what we're talking about here in terms of where it is in Thunder, in the Thunder code base. So you can see, and I always argue that this is potentially the best way you can learn what Python does under the hood, like not just the Thunder sausage, but the Python sausage. So if you go into Thunder core, very core, you have this file called interpreter, which is just any, one more file, yet another file. But you can see it's pretty bulky, right? It's like 7,370 lines. And this is the whole interpreter. It's not 100% coverage, but it has pretty decent coverage of the Python language as a whole. And this will take bytecode from Python that you will see in a second. So it will take this machine kind of closer to the machine representation of a program and will execute it just like CPython does. And it has the same semantics. So the crazy thing here is that the team went in and made sure that the execution of CPython, which has a lot of quirks when it goes into kind of corner cases of things, has exactly the same semantics as this interpreter. So in the end, instead of looking into what CPython does, if you come here and learn from here what CPython does, yeah, I think it's a great way of understanding how Python works behind the scenes. One of the disadvantages here is that sometimes minor versions of Python will change the way bytecode is structured and interpreted. So we were chatting with Thomas before the episode, and he's looking into upgrading to 3.13, and there are certain things that have been changed, so they have some, will require some work.
Yes, so the official company-supported version of Python for Thunder is 3.10 still, but and most of our CI actually runs on Python 3.10, which was the initial version. But so my rule of thumb is that whenever the Debian unstable gets a new default Python version, I need to upgrade because it just annoys me for my local development. And so this happened recently that I upgraded my Debian, and yeah, now it's Python 3.13. Now I need to check it. But you will see that it implements basically almost everything, I think, except grouped exceptions or exception groups. But other than that, it pretty much covers all of Python 3.10, 11, and 12.
Yeah, it's pretty incredible if you think about it, right? One could translate it into Rust and have a Python interpreter in Rust, right?
Well,
like it's crazy. Yeah.
Yeah, but so one thing is that there are actually in the Python project, there is a project to specialize the bytecode more and translate bits of the bytecode to something that can be executed faster, right? And you see this in little details, like there is an instruction to load one local variable on the stack for the stack machine. And so interestingly, the people thought, well, yeah, if every bytecode instruction comes with some overhead, if we load two values at the same time, that will be faster. And so there's things like that. Or where do we need checking, and where can the compiler say, yeah, I know this is correct, I don't need more checking. But
let's take a look at how it works under the hood.
Yeah, let's
this is a reflection while you open stuff. This is a reflection on what we mentioned them, the leukocytes, and we'll take a look at the leukocytes. Some models require you to nudge the interpreter in the right direction, especially, for example, where there's control flow, data-dependent control flow that is not really essential when you're in compiler mode, for example. And so looking at this stuff also helps you understand what is a Luca side and how you implement it.
Yeah, I'm having a bit of a thing. Okay, now
here.
It doesn't want me to share the screen, the window, which I usually do, but only the tab. But
Okay.
I guess you can live with that, right?
Yep.
Okay, so let's get right to it. And should we have a function first, maybe?
Yep.
So what's your favorite function, Luca?
I don't have favorites in general, not even ice cream, let alone
Oh,
functions.
we can have here. Well, let's have a function that takes a string, and if the string is well, I don't know. If it's Luca, it says it returns
Side.
ciao Luca,
Yep.
or ciao plus s, and if it's someone else, we can just return hello. We don't know they speak Italian, right?
Yeah.
So obviously, if I say this with Luca, it gets ciao Luca, and then you have hello Thomas. But so how does this look at the bytecode level? So one thing you could either try to compile the Python source code, and actually the PyTorch JIT scripting that did that. But so it's funny because sometimes it's really hard to acquire the source code of something. And this is in particularly true for classes, because somehow like Python keeps track of where the source for function is, but not so much for classes. But yeah, so Python comes with this module, or the CPython, I should say. I will say Python, but it's really all very implementation specific. So if you look at the disassembly of this function, you can see like what this gets translated to. So we first load our local variable. The arguments get put into the local variables too. So we load this, and then we load the constant Luca that is here, and then we call the compare op, and we will see like how the compare op works, and then we can then we see that it like has a branch, a conditional branch. So if it pops the result of the compare op, and so if it is true, it just continues and falls through, and if it's like not the case, then it jumps and continues here, and then it goes to the hello part, and here's the ciao part, and we see, for example, that there's a binary add here. And so this is something that I mentioned, that those opcodes, they will translate back into function calls.
Something maybe that we can mention is the stack, right? So when you say load, where does it load it? And when it says binary add, where does it take the arguments? Because there are no arguments there.
Yeah. So if we look at the this Python org module, and I will just share the other tab here. We see that there's a description of like in the module that gives you the disassembler. There's a description of all the things, and so the thing here is that there is a called stack in Python, but this is not that. But in every function call, and in older versions like 3.10, it's also for frames. There's for try except blocks, there's a special thing. But so in general, for each function, there is a while the function is executed, there's a stack machine that has as instructions the bytecodes, and it has a value stack where all the operands get their value from. So load fast takes something from the local variables, which is basically an array. So it takes the 0th value and puts it on the stack. Then load const looks in the constants, which are also an array. And so here it loads constant number 1. And you might like take a guess what's constant number 0. I don't know actually. But so we can find out. But so it takes constant number 1 and puts it on the stack. The compare op takes the 2 values from the stack and then has an algorithm how it like compares, and it compares by using the if it's an equality, it compares by using this Thunder method, string dot equal.
Yeah.
And then the pop jump if false, this will, depending on the Python version, it will expect the Boolean or convert to Boolean if it isn't already. But it takes an
But what is that Boolean? It takes it from a value stack again. Right?
Yeah. So
because the previous operation put it there, right?
Right. And so this pop means it pops one value from the stack, and then it jumps depending on the value. Yeah. And here again, load const, and then the stack will be empty again, right?
Yeah.
And then load const, load fast will put 2 values on the stack again, binary add, takes those values, adds them again using a Thunder function. And then it puts the result on the stack. And finally, return value takes a value from the stack and uses that as the return value, and then returns from the execution.
Awesome.
So this is basically what happens. And we can inspect some of the things around around the constants and local variables if we check the code object. And so, for example, here's the code consts, and the magic thing that is also here in the const as the 0th index is just none. And then there's the 3 constants that we have explicitly in our program. Don't ask me what it needs the none for in this program, but that's just the way it is. Interestingly, like one of the assumptions that the Python bytecode interpreter does is that the compiler will be smart enough to not produce a stack underflow. So if you want to crash CPython, like getting it to execute bytecode that you crafted is a fairly good way to crash it. And before we wrote this bytecode interpreter, we tried to like modify the bytecode instead, and there we hit crashes when we weren't careful.
Yeah, it was a minefield. Yep.
Yeah, but so yeah, but now we can say we want to like execute it with our interpreter, and we can say from Thunder core import interpreter. And I'll try to only use the interpreter from Thunder here, and we'll see how it goes. And there is, of course, the interpreter in Thunder is used by the JIT. Originally, there was some naming confusion. We tried to clean it up. The Python interpreter just goes with interpreting, and the JIT does the actual translation from Torch to Thunder. And so we will try to produce a very Mickey Mousey toy JIT for that can like JIT this function. And so the first thing we can do is we can look at what interpreter.interpret does, and it's a bit of a lie because if we call it, we get a function back that is essentially the same function. And I can now call it, and it will do the same thing. So very exciting function here.
Because ultimately, if you look at the interpreter, yes, we interpret the bytecode, but then we call CPython again to actually execute the side effects, right? So to do the actual calls. So it ultimately we generated this through CPython, but not the way you would expect it, but after
right,
going through the bytecode.
right, and there are like things where we can do things with the interpreter that's interesting. And so we can do a thing that we call with provenance tracking, and then it tries to keep track of where all the values come from. And so that will be interesting. And if we do it, we get an error. And we need to provide uncacheable classes. I don't know why we don't have like like the
Easy mode
classes as a reasonable default. But so let's put int bool and float here. I don't know. Maybe there's more of them. But so now it runs again. And so this like does the same thing, but internally it keeps track of all the things that we did, and we can like get a glimpse of this by asking it to not unwrap the result. So the tracking of the provenance will be done through wrappers of every Python value. And so if we do this, what did I now do now?
Results.
I'm using an old version of Thunder here. I think I changed something in this code like a little while ago, and maybe it's still the old code. That's how thoroughly we test all these things during Visual. But of course, not too bad. So we're at main, we pull it, and then we can try to start it.
So provenance conceptually is the notion of where values are generated, right?
Yeah. So now I get the wrapped value here, which is like the administrative thing from the interpreter, and we will have to deal with that whenever we grab a value directly from the interpreter. And so what you can do,
because it's a value, but it's enriched with tracking that the interpreter does, right?
So we can get the original result by unwrapping, but we can also like access the provenance, and that is a bit interesting. So this has a provenance record that tells you exactly, and it gets a bit better when you print it. That this came from a binary add opcode, and there's not that much interesting information here. But it will, for example, tell you if you have an argument directly, it will tell you that it's an argument. So if I just return S here, then we see that it's like from the input arguments, and it's the 0th input argument, like this one here. And so this is, this is what we have here. So this is good, right?
Yeah.
But now,
so we didn't change, contrarily to other approaches, we didn't change the value themselves, but we kind of wrap them inside something that we use to track, and the values themselves are kind of pristine, so we can get them out just as if CPython generated them. Somehow.
Yeah, but actually it is like good to also help the values kind of inside the interpreter. So in order to do this, we can define a string proxy class. And because it should be like a string, we will actually make it a subclass of string, which is a very neat like thing in Python. So we need to supply a way to create a new thing here. And this gets, even though it's not declared a class method, it gets the class. And we call the string new function with the class and the arguments. And this is like Python magic. But this will create a string proxy that you can use as a string. And note that I like took the keyword args here, but these are the same things that will be fed to the init method after the object creation. And so we can have here like additional arguments. And let me just take some. But so here we can now like have a name for the proxy. So we will have a global name counter, and the names will not be terribly creative. So we will increment we need to declare global, right? And then we need to get the name. So self.name is like S and the name counter, right? It starts with S0 and then just increments. And we will, and now we need to increment the name counter. And yeah, so let's keep track of the type. And
we're basically
I should have said something about this before.
Yeah, what is a proxy, right? So we are preparing things so that we can store them somewhere else and keep track of variables and function calls.
Well,
right?
In particular, what we want to get from the proxy, and this will where the type and argument will be handy in a bit. What we want to get from the proxy is a representation of the thing when we write programs. And that's the main thing I want to do here with the proxy. But so how do we use the proxy? And this is now one of our intervention locations, is that we can say when the Python interpreter like interprets bytecodes, it sees this code object here with the constants. And then it needs to, like, when it sees a load constant, it needs to like track the value. And so what we can do is we can hook into where it initially sees this and wraps it. And so this will be the wrap callback. And we can, for example, check here. Well, we can print the provenance, and we will see provenance. And we will see it's like a lot. This will be a wrapped value. Maybe I call it WV. Mm-hmm. And then we need to tell the interpreter that we have this awesome callback, right? And so we will have here a parameter callbacks, and this will be interpreter, and this is just like a dictionary interpreter, and the keys are like called interpreter callbacks. And so this will be, and we see here we have a number of them, but the most important one is the wrap callback. And so we hook into this. And one thing to know here about Python is that it uses a lot of values here. So if we run this, wrap callback is not defined.
Const.
that was not the right thing. And so we see we get a lot of things here, right? Like every value that Python touches during the execution of this short program is recorded here. So we don't want all of these, but we just want the strings, right? And so, and maybe not all strings either, but only the ones that interested us. So we can check what the provenance instructions are. And so if this is interpreter, if it's a constant, we want to like wrap it if it's a string constant, right? So if the interpreter is if the provenance instruction is this constant and the unwrap interpreter unwrap of the wrapped value if this is a string.
Yeah, it's interpreter in the same line.
Right. Maybe I put this in an if here, and maybe I can close this. Then nice. I have more space. So if the interpreter unwrap, if that is a string, we can, and maybe we even do, do we want to have subclasses here? Let's be safe. And so if it's a constant,
it's type, right? It's type.
Sorry?
In the previous line, yeah.
Okay. And so if this is the case, we want to register a proxy for it. So the rep value allows to register a proxy, and this will magically switch the thing while keeping track of where it came from. And so what we have here is a string proxy, right? And we want the original interpreter. Unwrap of the wrap value and the tip.
Yeah, we need to unwrap because we need to store, we need to initialize the proxy with the actual string and not it's wrapped. You know, if you remember this, that the compiler will always wrap because it needs to keep track of things. So whenever you need to access the value, you unwrap it. In this case, we are unwrapping it, taking the proxy, which will be the thing that can populate our trace in the future, and then initializing the proxy with our raw value, and then the compiler will wrap it back. But now you'll have a wrap proxy.
Right.
I hope this makes sense.
And so we just have the string as the value, right? And if it's not a constant, we can still print the provenance, maybe.
Yep.
And so if we run this, it takes a while. What happened here?
Infinite recursion?
Yeah, it looks like it, right?
Yeah.
But I don't actually see where this would be. Maybe we restart it and see what's going on.
Okay.
Somehow it seems to be like sort of slow today. I don't know what it is.
Okay, now that's done. Oh,
Okay,
nice. All right.
now we get all sorts of things. And so what we can do here is we can have a print function. And so we can print this as if self tip equals const. If it's a constant, then we return like the representation, and this will put strings into the quotation marks, right? And so here we raise not implemented error. Okay, so this takes care of constants, but the other type of value we're interested in is the arguments here, like these
Yep.
guys. And so we can check that too if we want. So if the provenance inst is interpreter pseudo-inst get item, I think. No, binary subscript. Binary subscript. And we want to know what it is a subscript of, and what's a subscript of is provenance inputs, and the 0th item will be here the 0th item will be the input args, and so we can check if that is an input arg. And then we also register a string proxy for it.
Yeah, where it is another type, obviously, but the value would be the
and
one.
the type should now be arg, and the argument should be VW provenance inputs, and the first input will be like
the value of that. Yeah.
right? And so we can do this too, and now we can get rid of the print. I always like debug prints and have to remember to take it out from the PRs. So what did we gain here? And we need to like be able to print those too. So self type, if it's an arg, then we return args and self.arg. Right? And so this is it. Oh, if we don't have any of this, we return, and this is like, yeah, this should be an if, and then we return self.name actually. So we just return the variable name of the proxy if you want. And so this will be if we follow this now, if we have a string proxy, we can print it. But so far we haven't like tracked the actual functions that happen. And so one thing we want to definitely check out is the binary add. And so I mentioned that those map to Dunder, and so this maps to string add. And so we want to actually redirect add. So we could now like hook this into the string proxy, but there's also another method, and this is the lookasides. And we had this in a bit. We had this a while ago. They always play a when we want to like redirect something, typically some function call to make a Thunder version of it. But so here we can have the look-aside lookup, and it will get a function, the function that is about to be called, and the args and the keyword args of the function. And with that, we can like check what it is. So if the function is string.add, we can return like a different function, and let's call this the string add.
Yeah, let me summarize what's happening here. Right now, we have created proxies for the values so that we can enrich our representation of what's happening to the values of the computation. Right now, we're defining alternative implementations of the functions that are triggered whenever the bytecode reaches some function to execute. So we can actually extend our interpreter with a custom specific function that will only happen when we decide. So in this case, with string add. And so when we meet that, instead of like letting the interpreter execute what it's supposed to execute, we can enrich that. And that gives us the ability to also record the fact that the function is executed. And really, this is the gist of how we go from interpreting a model like R1 and the trace that will be generated by keeping track of all the inputs that we care about, which are tensors and numbers and constants and all that kind of stuff, and the operations that are called, which in our case are mostly, but not only, torch operations, right? Torch functions. And we can replace those torch functions with other functions that operate on metadata and don't actually execute the function immediately, but we can reason about that. And so that's how we get the trace. And then there are many other details here. But essentially what Thomas did right now is to have a look-aside, a custom implementation of string add that takes the interpreter, unwraps the two arguments and returns, checks if we're dealing with string proxies.
Right.
And then, yeah.
And now we can have a string proxy for the result, and this will be string A plus B. And so there will be no string proxy here, and this plus will be executed by the standard Python interpreter and not by our one, right? So
and also you could also decide not to execute it, right?
Yeah, I could.
But in this case, it would create a problem because you would have a result that you can't really the program may depend on the result and so on. But if the program doesn't depend on the result, right? If the rest of the program doesn't depend on the actual result of A plus B, you can only track the fact that there is an A plus B between two things. And this is what we call data dependent control flow. And in terms of deep learning programs, we only mostly care in the compiler what happens to metadata, which is d-type, the shape of the tensor, but not the numbers that are written in there. And so our look-asides will translate to functions that do not care about what happens in the values of the tensor, but only to the tensor as in their metadata. And this is really where the magic happens.
Right.
Yeah.
And so I probably could have made it easy for myself by let's do that.
Yeah, we have 5 minutes. We're coming to the hour, so this was a long one, but at least this is really how the sausage is made to the finest degree. We went down to the very low thing, but if you understand how this process happens, you basically understand how Thunder works in generating.
I didn't. Why does it not why doesn't? Oh, I didn't provide here the look-aside.
Yeah. And so if you then implement a recipe, and we'll present recipes, but we're coming out with recipe officially at GTC, so in a few weeks. Some recipe will have look-asides because some models will be quirky. You have some Hugging Face super complex implementation, and there might be pieces of it that are not compiler friendly because they contain some, I don't know, some constructs that are not compiler friendly. You can sidestep them writing a custom Luca site for certain things. And so this looks like very deep, but it also percolates up, and you will see some recipes having Luca sites that are custom for that model or that implementation.
So here we have now recorded like the instruction that got us this string, right? And so actually we can now also print like the result, and this will be actually also a proxy, and so we can call the print method from interpreter unwrap result, and we see like this is the thing, and I would need to add a return. And I can also check like this equality check we have at the beginning of the function. Mm-hmm. I can check this. I can override this equals with a look aside that will record like here was a comparison, and you need to do the comparison. And this is what Thunder does, and it puts all these checks in the prologue, and then we can have it here. So
yeah, because ultimately, if a check changes, then your control flow in the function might change, and the function may go another way, right? And so you will know if potentially something has changed by getting all those comparisons, evaluating ahead of time, and if they all check across the function, then probably your function hasn't changed. And so you may also not retrace it. You want reinterpret it. But if those checks are the same, you reevaluate them, they have the same value, you can just jump ahead and say, okay, let's re-execute the trace without caring about the program anymore. Right. If some of them are invalidated, you need to retrace, or you can do something smarter and avoid retracing everything. Like you fantasy, like sky is the limit there. But it's good. Like we created that list that was at the last line is the first, like it's a trace. It's a list of things, right? Yeah. It's a minimal trace. And this is how Thunder works. And conceptually, it's very complex in practice because there are many cases to cover, and Python is a complex language. But conceptually, this is all there is in the interpretation.
Right. And so that's how we get the programs in Thunder, like go through them one bytecode at a time. Yep. And there's a lot of them sometimes because there's a lot of indirection in Python itself, but also in Python, which, and you can see that from the stack traces that you sometimes get, right?
Yeah, exactly. Yeah, very long ones. All right. Thank you so much. This was a long episode, but I'm glad we covered this because it really is the heart. And so there will be no mystery, or almost, when you need to write a look aside for your next esoteric model that you deal with. All right.
Okay. Thank you, Thomas. So it's evening now, so it's dark outside.
Same here.
Time for the weekend.
Yeah, exactly. Bye, everyone. Thanks for following.
Bye. Bye. See you, Luca.